Problem 2. A 200-gram block is traveling to the right at a speed of 5 meters per second toward a spring with a spring constant 575 newtons per meter as shown in the diagram above. It runs into the spring, compressing it, and then is pushed in the opposite direction by the spring, where it travels up an incline at 30 degrees to the horizontal. All surfaces are frictionless. A. Calculate the maximum compression of the spring, and B. Calculate the distance the block travels up the incline. Alright, so the first thing to do is to understand what's going on in this problem. So let's take a look at this. So we have a block that's traveling to the right. It runs into the spring, it compresses it, and then the spring pushes it back to the left. It slides up the incline, then comes back down the incline, and the whole process repeats. Because there's no friction, this process would go on indefinitely. Alright, now that we know what's happening in the problem, let's try to identify the type of problem. There are a few features here to note. We're not asked to find time, and we're not given a time. There are no vectors in the problem, and we're not asked to find any. For example, in problem 1, we're asked to find a direction for the final velocity. And another big characteristic of this problem is it involves springs. With these characteristics, this identifies the problem as a work energy theorem problem. And because there are no non-conservative forces, this is actually an energy conservation problem. Which means we're going to use this equation. In an energy conservation problem, we want to identify different positions which occur at different times in the problem. Let's take a look at the block at different positions in this problem. We're going to call this position 1, this position 2, and this position 3. So for part A, calculate the maximum compression in the spring. We're going to go from position 1 to position 2. So this is our energy conservation problem. So we have a kinetic energy in position 1 of 1/2 mv squared. And in this problem we have two types of potential energy. There is gravitational potential energy, so mgh for position 1, and because there's a spring in the problem, there's also a possible potential energy for the spring. And then in position 2 we have the same thing, just with subscripts of 2. Now to plug in values for this, we need a coordinate system. So let's go back up and put a coordinate system on this problem. So I'm going to choose the center of the box in position 1 to be the origin. And really all that's important in this type of problem, because we're working with gravitational potential energy, is the y position. Where do I set y equal to 0? So I'm going to call this position y equals 0. So now in position 1, my height of the box is 0. And in position 2, the height of the box is 0. In position 1, the spring is not stretched or compressed, so delta x1 is 0. But in position 2, the spring will be compressed. And that's what I'm looking for. This is what I'm looking for in part A. In position 2, the box is not moving. The spring is at its maximum compression. There's no velocity of the box in position 2. So this energy conservation equation simplifies to this. So the compression in spring at position 2 is going to be simply this. So the spring compresses a maximum amount of 9.33 centimeters. Part B, calculate the distance the block travels up the incline. So in a similar way, we can say that the energy in position 1 equals the energy in position 3. So in position 1, I have a kinetic energy of 1/2 mv1 squared plus mgh1 plus 1/2 k delta x1 squared. And again, in position 1, the height is 0. And when the block is in position 1, there's no compression or extension of the spring. In position 3, I have a kinetic energy of 1/2 mv3 squared, a gravitational potential energy of mgh3, and a potential energy of the spring of 1/2 k delta x3 squared. In position 3, the spring is neither stretched nor compressed. Also in position 3, the block is not moving. It's at its maximum height, turning around, getting ready to come down the incline. So V3 is also 0. There's no kinetic energy. So here the equation for energy conservation simplifies to this. And we have H3 is V1 squared over 2G. So when the block stops on the incline, it has moved vertically a distance of 1.2755 meters. The question asks, though, how far along the incline does it move? Here is what we have. We've calculated H3, but we want to know this distance. So the block moves along the incline a distance of 2.55 meters.